In this video, I'm going to be talking about how to do a free body diagram and how you know when to include each of the different forces and each of the different scenarios. So let's take a look at this woman being pulled in a sled first. So we want to make sure that we concentrate on a specific thing for each of the pictures. You could draw a force diagram on the man pulling or on the woman or on the sled. So we're going to call it the woman sled system. So you want to make sure we're focused on a particular thing before you get started. Now we have a few different forces in this case. I would say the first one we typically are going to go with is the force of gravity pulling straight down towards the center of the earth. Okay, that one you're basically going to include every single time unless you're talking about some objects in space. In that case, you would have a force of gravity towards the masses that are next to it. But I'd say in most regular cases, you basically just have a force of gravity straight down because of the pull from the Earth. Now, technically, the way the force of gravity works is it is the center of gravity, which is basically like the center of the system, being pulled towards the center of gravity of the other object. But for pretty much all diagrams, you can pretty much say it's straight down, and that's going to work for you. The second thing is because the sled and a woman system is being supported by a surface, that surface holds it up and counteracts the force of gravity. We call that the normal force, Fn. Now, normal actually means perpendicular. So I would normally define that as a perpendicular support force. So how are you going to know that's there? If it's sitting on or against another surface, it's pretty safe to assume that there's going to be a force pushing up perpendicular to it. For our third force, we have a rope tugging the system. Okay, anytime it's something along the lines of a rope or chain or string, we call that Ft, the force of tension. And that is always some kind of pull. And then I'll say from a rope like object. Okay, so something along the lines of a rope, a string, a chain, something that when you cause it stress, it stretches out and then there's tension in it. And then the third one is assuming that the entire system is sliding to the left, then we have a force opposing it. And then that's we're going to call FFK, the force of friction, and then specifically kinetic. So we'll call that kinetic friction. And this is something that always opposes a slide. So anytime something is sliding because of the irregularities in the surface, no matter how smooth something is, there are slight irregularities that may be invisible to the eye that are going to basically be scraping and pushing up against the thing that's sliding across. It always opposes the slide, so it's in the exact opposite direction that the thing is moving. Okay, to recap this one, there are 4 different forces there. We have force of gravity, which is always straight down. If there's any sort of mass, if something is on a surface, we have a force perpendicular pushing it and supporting it. And then if there's something pulling it that's like a string or a rope, we have that force of tension. And if something is sliding in any which way, in the exact opposite direction, we have the force of kinetic friction opposing that slide. Okay, let's go ahead and take a look at the second one over here. For the second one, we're just going to focus on this mass over here, this orange box. And we're going to take our first rule. We're going to take the force of gravity straight down. So although something is on an angled surface, gravity isn't going to pull on an angle. And then because it is sitting on a surface, we're going to go with the normal force. Remember, the normal force is perpendicular. So this one is actually angled because to make a 90-degree angle with this ramp, we're going to have to make sure that we sort of angle our vector a little bit. And then we have a person pushing it. That one is going to be a little bit of a new one. And if they're pushing it, then their force is directed this way. We're going to call that FA, an applied force. Okay, since I don't have too much room over here, I'll write in a little note over here. So FA, I would call it some sort of direct push or pull. So that one is kind of like a general one where if you have a thing pushing or pulling it that isn't necessarily a force of tension, we can call that an applied force. And then if it's sliding up the ramp, remember the force of kinetic friction goes opposite of the direction that the object is going, assuming that it's sliding on the surface. Okay, now going to our third one, we have a kangaroo jumping up in the air. And a lot of times people would think of putting an applied force upwards, but forces have to be applied by another object. For example, force of gravity is by the earth, force of tension is by the rope, the normal force is by the surface, the force of friction is also by the surface, the irregularities in that surface. Okay, so for this one, it would be considered in, whoops, I left my eraser on. For this one, it would just be force of gravity. So you have to be careful when objects are moving a certain direction that it doesn't necessarily mean that there is a force being applied in that direction. If a kangaroo jumps up, did they probably apply a force on the surface? Of course they did. But then as soon as they're in the airborne or in a airborne position over here, then we just have the force of gravity pulling straight down. That would be considered something that's in free fall, only having the influence of gravity. All right, now taking a look at our last one, we are going to take the person from the center, give them a force of gravity straight down towards the center of the Earth. And then this one has sort of an interesting case because they're standing on the ground, so the ground is supporting them with that normal force perpendicular surface. But then additionally, he's leaning against a wall this way. So this one is pushing out perpendicularly to support his back as well. So we have two normal forces. And then the third one I'm going to add is on his foot over here. So we actually have another type of friction. Okay. Now, if you think about the forces, the person is at rest. Therefore, that means all of the forces should be canceling out and the net force is zero. This Fn over here, the vertical one upwards, is canceling out this Fg. And then there's an Fn pushing him to the right. And if he's not moving or accelerating to the right, there must be a force to the left, which there is. We're going to call that FFS, the force of friction static, more commonly known as static friction. Okay, this is for something that's trying, or we'll say opposing, and it's something that's trying to slide. Okay, so it actually has the same kind of effect that kinetic friction is. Kinetic just means in motion. So when something is actually sliding, it's pushing back in the exact opposite direction. This one is when something is trying to slide. The foot is trying to slide to the right, and it is not. That means that the rubber on the sole of his shoe and the surface are interacting with each other and pushing back to the left. We call that the force of static friction. Okay, keep in mind all things that are static and not moving don't necessarily have static friction, but a car parked on a hill or a person leaning against the wall with their foot pressing on the ground, those have static friction because it's something that's trying to slide. So ask yourself, is it trying to slide? And if the answer is yes, then we have the force of static friction. So those are the main forces you're going to see on these free body diagrams. I actually didn't separate them from their environment because normally I guess a free body diagram would be taking the object and separating it from the environment from the picture. But I think in this case, it's helpful to kind of see the environment to realize where the forces are coming from. In this video, we're going to be taking a look at a couple masses that are attached to a string that are all in equilibrium. And we're going to find an unknown mass of this blue block right over here. So the first step we're going to do is we're going to go ahead and draw our forces acting on both of our masses and on this intersection of where the strings meet as well. All right, now we have all of our forces acting on both of our masses along with this main intersection over here. Now, although this isn't particularly a mass that people would concentrate on, that is the point where all the forces are sort of interacting. It's like the central point that's in equilibrium that's keeping the entire system at rest. So if we have a case in equilibrium, we know that the net force in the horizontal and vertical direction are going to be 0 newtons because there is no movement, velocity, or acceleration of any sort. Now, with that in mind, we want to analyze the system and figure out what are the important vertical and horizontal pieces of it. So we want to make sure we take this one angled force and create an FT2x and an FT2y, which is basically our x and y component of each of these. Now, this looks a lot more complicated than it actually is, but we know that this FT1 over here is the same as this FT1, and this FT1 is the same as this FG over here. These ones are going to be equal and opposite of one another, or else the object wouldn't be at rest. So we know that this MG, whatever it may be, equals FT1. And then also our FT3 over here is equivalent to this FT3 over here. And this FT3 must be equivalent to this force of static friction, again, because it's at rest. We know that the FT3 equals the force of static friction. So we know the force of static friction on our 3 kilogram mass is equal to our FT3. And then also in our angled rope over here, we have our X and Y components. So we can go ahead and write out some formulas. So we have the sum of forces in the horizontal direction. And if I'm taking a look at all the forces to the right, I only see this FT2X. And I'm taking a look at all the forces on the left. It's basically this FT3 pulling on that intersection. And we said this FT3 is the same as this FT3, which is equivalent to the force of static friction. So it's basically subtracting the force of static friction equals 0 newtons. Also, the sum of forces in the vertical direction, again, where our main focus is at this intersection right here, we take a look at all the forces pulling up on this part right here, which is just our FT2y. And then the only force that's pulling downward is this FT1. And again, this FT1 is the same as this FT1, which is equivalent to this FG over here, which is just mg. So this m is our unknown. And then I can go ahead and put in 9.8 for my g just to have some more numerical values, equals 0 newtons. Okay, so let's go ahead and plug in some number values. As of now, it doesn't seem like we have much information, but generally what you want to do is just start with your force diagram, write your equations, and then put in any numbers you know at all, and that will typically lead you one step closer to the solution. So let's go ahead and do that. All right, so where we're at right now is we have the FT2x of 8.82 newtons. The force of static friction is the coefficient of static friction, which is 0.3 given to us, and then times the normal force of that 3 kilogram block. We know that the normal force over here is going to be the same as this FG3 because those are the only vertical forces, and there is no movement in the vertical direction or acceleration of any sort. So we could just say 3 times 9.8 is 29.4 for our mg, so that is our Fn. So then we did mu s times the normal force, and that gave us 8.82, and then add that to the other side. So our Ft2x is 8.82 newtons. Okay, now that's really good news to us because we have this triangle over here, and we have a 30-degree angle. Anytime you have one side and one angle of a triangle, that's good news because you can find any other side of the triangle as well. So let's go ahead and redraw this triangle on the side where there's a 30-degree angle, and we just found out the x component is 8.82. And I'm most interested in finding this right here, our y component, which will be too hard because we have everything we need. So ft2y is right over here. So we have the opposite and adjacent sides that we want to utilize, which means that we're going to use the tangent of 30 degrees, and that equals opposite, which is our ft2y, over our adjacent, which is 8.82. And then we basically multiply both sides by 8.82, and then we have our FTY, which comes out to 5.09. So now if we know this is 5.09 newtons, we can add this mg to the other side, so equals m times 9.8. And then just finish off dividing both sides by 9.8, and then we have our mass. Okay, so when you're working on a problem like this, if you have a certain point, such as this over here, it may not necessarily look like it's the focus because there's some other masses in the problem, but that's the point where everything is pushing or pulling. Therefore, that would be your focus of your equilibrium problem. And a lot of times that some of these forces are all connected to one another, such as this FT1 and this FT1 and this FG. And then you can kind of simplify it by seeing what things are equivalent to each other and then creating some formulas from there. We're going to be taking a look at two masses that have an 80 Newton angled force applied on it. The first one has an 80 Newton force angled downward at 30 degrees, and the second one has the 80 Newton force angled upwards at 30 degrees. So we're going to compare and contrast these two situations to see which one has the greater acceleration and why. So let's go ahead and take a look at our first object over here. We have a bunch of different forces acting on it. So we're going to start off with drawing our force diagram on here first. We have Fg, force of gravity, pulling it straight down. We have the normal force pushing up perpendicular from the surface. And then we have this force over here, which we'll call an FA, an applied force on the mass. And then because the object would be sliding to the right, we have a force of kinetic friction that would be opposing the slide. And in addition to that, I'm going to slide this right below it. If we want the force of friction, we're going to do the coefficient of kinetic friction times the normal force, which we're eventually going to use a little bit later. Now, a couple things are this. We want to set up the forces in the x and y direction. In the x and y direction, we have Fn and Fg, and then we have this angled force over here that we want to break up into two different components. We have a y component here and an x component here. So let's go ahead and pull that triangle aside. So that we can solve for those x and y components. Now, our 30-degree angle is over here because it's 30 degrees above the horizontal. So the end that's opposite of that is going to be our y component. So we can call that maybe FAY to be more descriptive, and we'll call this one FAX. So since we want to use the 80 newtons actually, 80 newtons as our hypotenuse, along with our opposite end, we're going to use the sine of 30 degrees because sine is the opposite over the adjacent side. So if we go ahead and set that up, then we have the sine of 30 degrees equals the opposite over, basically multiply both sides by 80, and then 80 times sine of 30 is going to be 40 newtons. Now, the second thing we're going to do is we're going to do the same thing for the x component. We're going to go ahead and use the adjacent side to the 30-degree angle, and we're going to have FAX over 80 newtons equals the cosine of 30, and then do the same thing, multiply both sides by 80, and then that gives us our x component. Our x component comes out to be 69.28 newtons. All right, so that's the first thing you're going to want to do. I'm going to go ahead and include both of those values right up here so that I can clear some space to show the work for both of these two larger calculations. So we got the FAY is 40 newtons, and then we have an FAX of 69.28. All right, so let's go ahead and clear this previous work and then set up our formulas for everything in the X and Y axis. So now that we have our two formulas set up, we have everything in the upwards direction as positive, which is only Fn, and anything that's directly downwards, which is our Fay and our Fg downwards. So we're subtracting those two, making those negative values equals m times a, and there is no movement or acceleration in the vertical direction, so we can say that's 0 newtons. In the horizontal direction, we have our Fax pushing it to the right, and then we have our FFK, our force of kinetic friction, opposing it going to the left, and that equals m times a. We know that m is 10 kilograms from the original question. That's where we're going to be able to solve for our a. So let's go ahead and plug in all of the values we know and see where that takes us for our next step. Now that we plugged in everything, everything fell into place pretty nicely because we don't have a normal force. We know that Fg is mg, mass times 9.8, so the mass of 10 times 9.8 gives us 98 newtons. And then the Fay we found earlier, which is right over here, 40 newtons. So then we know that if we combine these two, then it's Fn minus 138. You add 138 to both sides, and then your normal force comes out to 138 newtons. Now for our second formula, all of our forces in the x direction, we have our Fax that we found earlier right up here, minus force of kinetic friction. Kinetic friction is mu times normal force, as we stated earlier. The mu is 0.2, which was given in the original problem over here. And then we actually just found out our Fn right here, so that 138 was very useful. And then now we have everything we need except our acceleration. So if we just divide both sides by 10, then we end up with a final acceleration of 4.17 meters per second squared. All right, now we're completely done with this setup over here. Now let's go ahead and analyze the second one. So the second one, we basically have the same triangle. It's 30 degrees above the horizontal, but pulling upwards. So the main difference is going to be this. We have an Fax going this way and an Fay going that way. So really the only difference is the Fay. So if you take a look at this horizontal component, it's going to the right. This horizontal component is going to the right, but this vertical component is pushing downwards and shoving the mass more into the ground. And then this Fay is pulling up a little bit and releasing some of the force of the mass is applying to the ground. So we're going to basically set up the same exact formulas. It's going to be the sum of forces in the y direction is Fn minus Fg, but then this time a plus Fay, because this one's going upwards like our Fn. That still equals 0 because there's no movement or acceleration in the vertical direction. So our Fn is still unknown. Our Fg is still 98 newtons, mass times 9.8. And then this time we're going to add the 40 newtons as opposed to the first one where we subtracted it right over here. Okay, so that equals 0. So this time our Fn is going to drop quite a bit, and it's going to be 58 newtons. And as I said before, the Fay is helping the normal force support the mass so that the normal force doesn't have to work quite as hard pushing upwards perpendicular from the surface. Now let's go ahead and work out our second part. We have the Fax still driving the mass and the FFK still counteracting it. So this is still going to be 69.28 to 8 newtons, and then minus mu times our new normal force of 58. Okay, so obviously this one is 0.2 times 58 as opposed to 0.2 times 138. So there is much less friction. So that means that our mass should be accelerating much faster. So once you subtract these and divide it by 10, your acceleration comes out to 5.77 meters per second squared. Okay, so we found our final answer. The second one is the one that's accelerating more, which the reason being is right over here and right over here. Because of this upward FAY, it helps the normal force, and then the normal force doesn't have to work quite as hard to counteract this 98 newtons. So it shrinks the normal force, and the normal force shrinks the force of friction because the force between the mass and the surface of the ground isn't quite as much as when it was pushed downwards into the ground. So then that's why when you subtract this smaller value of friction, you have a greater net force. So when you divide by 10, you have this greater acceleration of 5.77 meters per second squared. In this video, we're going to be looking at two blocks that are being pulled by a string that are also attached by a string in the middle as well. We're going to solve for the acceleration of the whole system, each block, and the force of tension of this string holding the two blocks together. So the first thing we're going to do to solve for our acceleration is treat this like one big system. And I'm going to treat the 5 and 3 kilogram block like one 8 kilogram block. As usual, we want to analyze our object by drawing in all of our forces. We have the force of gravity down and the normal force up, which are equal and opposite of each other, which isn't the case all the time, but since they're an object sitting on a flat surface with no other forces in the vertical direction, they are equal and opposite of one another. In addition, we have this force of tension to the right and the force of kinetic friction opposing the slide to the left. So we're going to take a look at the sum of our forces in the x and y direction first and go ahead and draw out those formulas. All right, in the y direction, we don't have quite as much to look at because we have no movement or acceleration in the vertical direction. So we have the normal force minus the force of gravity equals m times a, which equals 0. So Fn would equal Fg if you added Fg to both sides. In the x direction, we have the force of tension, which is this big, well, not so big, 35 Newton force to the right. And we have the force of friction opposing that slide, and that equals the mass times acceleration. But since we're looking at both objects as one big system, we have 8 kilograms in total with some kind of acceleration. We do know the force of tension is 35 newtons, and the force of kinetic friction is always mu times normal force. So mu, the coefficient of kinetic friction, is 0.3 according to our setup right here. And then our Fn is equal to our Fg. So Fg is mg, which is mass times 9.8. If we take 35 minus the product of these is 23.52 newtons. That equals 11.48 newtons total, equals the 8 kilograms times the acceleration. Divide both sides by 8. And then we have an acceleration of 1.44 meters per second squared. So that's the acceleration of the entire system. So if you were asked for the acceleration for the 5 kilogram or 3 kilogram block, both of them would have an acceleration of 1.44 meters per second squared. Now what we can do is if we analyze each of the boxes on their own, as their own separate systems. We have the 3 kilogram block that has an FT going to the right. We'll call this FT1. It has the force of tension pulling it backwards. We'll call it FT2. Force of kinetic friction because it's sliding. And then we have our vertical forces, again, which aren't as significant. Force of gravity down, normal force up, which are going to be the same value, opposite directions. For our second block, we have this same force from this string, FT2, the tension, except this one is pulling it to the right. We have the force of kinetic friction opposing the slide. And then we also have the normal force and the force of gravity that are equal and opposite to one another. So what I'm going to do is I'm going to set up the sum of forces in the x direction for the 3 kilogram block and the 5 kilogram block. Then we can go ahead and solve for the FT2, the tension between each of these strings. All right, so I have the sum of forces in the x direction for each of them, and where our original acceleration comes into play is on the right side of the formula where we have m times a for each of the individual blocks. So that's going to be helpful into it for us to have all of our values on the right side of the equal sign. Now, if you wanted to find FT2, you wouldn't necessarily have to solve both of these formulas. Both of them, the FT2 should theoretically come out to the same exact number. If I were to choose one, I would probably choose this formula in blue only because it has less variables in it. Other than that, they're really not too much different in difficulty for solving for FT2. So let me go ahead and solve for FT2 down here. So that's our main unknown variable, and then we're going to subtract the force of friction, which is the mu times the normal force. Remember, the normal force is the same as the Fg, which is mass times 9.8. And that equals mass times the acceleration, which comes out to about 7.2 newtons. So then we have our FT2 minus the product of these numbers, which is 14.7, equal to 7.2. Add 14.7 to both sides. And we have a force of tension of 21.9 newtons. So if we just wanted the force of tension of this string in between the 3 and 5 kilogram block, we'd already be done. But let me go ahead and show you how the numbers are going to work out with this formula too, and then we'll see if we get the same value. So we have the FT1. Actually, we already have the FT1. It's 35 newtons minus the FT2, that's our unknown, minus coefficient of kinetic friction times Fn, which is the same as Fg, which is mass times 9.8. So now if we multiply some of our values, we have 35 minus FT2 minus 8.82 equals 4.32 newtons on the right side. So if I add 8.82 to both sides and then subtract 35 from both sides, I would have minus FT2 equals negative 21.9 newtons rounded off. The negatives would drop out. And then I would get an FT2 of 21.9 newtons, which is going to be the same number as the one that I got earlier. So when taking a look at a problem like this, it's beneficial to take a look at it as one big system so that we can solve for the acceleration, and that acceleration was extremely helpful in plugging in over here and here to solve for different values, such as our FT2, the force of tension of this string in the middle. In this video, we're going to be taking a look at an object that is pushed up a ramp with a force of 50 newtons, and then we're going to solve for the acceleration of the mass. Now, the first thing we're going to do is go ahead and draw the forces acting on the 5 kilogram block, which is the force of gravity pulling straight down, the normal force pushing straight up perpendicular from the ramp, and an applied force of that 50 newtons. And then, assuming that there's friction being considered, we have the force of kinetic friction opposing the slide. So the first thing we're going to do is break our force of gravity into its components so that we can use it in our formula. And we'll call those FGY for our perpendicular component and FGX for our parallel component. This 30-degree angle is always going to translate into this part of our right triangle. And then we can go ahead and do a little bit of trig to solve for that FGY and FGX. So let's go ahead and do that first and then set up our formulas afterwards. Okay, so what we did is we used the sine of 30 degrees, which is the opposite over the hypotenuse, and our hypotenuse is FG, which is equal to mg, mg being 5 kilograms times 9.8. That's where the 49 newtons came from. And then we found the opposite end, the FGX, by cross multiplying the 49 over, and we got 24.5. And similarly, we did that for the FGY, but we used the cosine of 30 degrees so we can find the adjacent side, which gave us this perpendicular component. Okay, so now that we got our components, we can find our sum of forces along the y and x direction. So along the y direction, we have the normal force pushing up, and then we have FGY going down, which is equal to 0 newtons because the mass is at equilibrium in the perpendicular direction. Now, for the sum of forces in the parallel or x direction, we have 50 newtons pushing it upwards. Now, one thing to be careful about is although the 50 newtons is pushing it upwards, that doesn't mean that the object is actually going up the ramp. The only reason I'm sure that is now going up the ramp is because the FGX that's opposing it going down the ramp is only 24.5. If that is higher than the 50, then the object would actually still be sliding down the ramp, although something is pushing it up the ramp. So because the 50 newtons is the winner between the two, we know that we're going up the ramp. So I'm going to call this my positive, and I'm going to say that my FGX is in the negative direction, slowing it down, and we have some friction opposing the slide, the force of kinetic friction. That is equal to mass times acceleration. So for our first formula over here, Fn minus Fgy, if we add Fgy to both sides, that means Fn is equal to Fgy. That means Fn is equal to 42.44 newtons because we already saw for that a little bit earlier. Secondly, we have our FGX over here. We know that it is 24.5 newtons because we found that earlier. And then for the force of kinetic friction, it is mu times normal force. Our mu is 0.3. So we're going to do mu times the normal force, which we got above. Then after we combine those three numbers, we get 12.77, and that equals our 5 kilograms times A. And then we go ahead and divide both sides by 5. And that leaves us with 2.55 meters per second squared as our final acceleration. So to sum things up, when you're doing a problem like this, you want to make sure you draw all of your forces and then break down your FG into your FGY and your FGX components. If you are pushing something up a ramp and that force is greater than the FGX, then it is traveling up the ramp. You want to make sure you take this as your main driving force, subtract the FGX, along with some friction if there is friction involved in the problem, and then you'll be able to solve for your acceleration. Now, if the problem is something that is moving down a ramp, then we'll just say that this 50 newtons is not present. And basically what you would do is you would do FGX minus the force of friction equals MA, and then all the rest of the steps would be exactly the same, and you can solve for the acceleration moving down the ramp as well. In this video, I'm going to be talking about how to do some different pulley problems, which are also known as Atwood machines. So we have a vertical pulley over here, and then we also have a pulley pulling an object on a ramp. If you wanted to see a pulley problem with an object being pulled along a flat surface at a 90-degree angle, then click on the link above. All right, so the first way to start off the problem-solving process with these is to always draw your force diagram first. So I'm going to go ahead and do that and then proceed from there. All right, so I drew the forces on each of my objects. I called these FGs FG8 and FG5, so I knew which force of gravity was which. And then I also did the same with the FTs. So you want to do two more things when working with a pulley problem. Number one, you want to identify which direction is positive and negative. So all along the string or the rope on an Atwood machine, you have to identify which way is positive and which is negative. So I'm going to say that because this is 8 kilograms and the rope is going to be pulled up and over this way and then downwards, that everywhere along this direction, I'm going to consider that positive. Okay, so that's not really typical of a lot of other problems where up is positive and down is negative. So everywhere along this direction of the pulley, I'm going to consider positive, and anything opposite that direction, I'm going to consider it negative. The second thing you want to do with a pulley system is identify what your system is. So my system is the 5 kilogram mass and the 8 kilogram mass together. So I'm basically going to clump up everything in here, and I'm going to say that whole system moving is the thing that I'm going to be analyzing. Now, the reason why that's important is because only forces that are external from your system are to be included in your sum of forces. So these two forces are inside of this green blob that I drew. So they're not going to move the system because there's all kinds of internal forces happening typically, but those are going to have a net force of 0. So we just want to look at the forces that are external. So this FG8 and this FG5. Now, according to the system that I set up, this way is positive. So my FG8 is going to be positive, and anything that goes this way along the pulley is going to be negative. So if I draw my sum of the forces, my sum of the forces are FG8 minus FG5, and that's going to equal M times A. Okay, so I'm going to go ahead and plug in my numbers, plug in my mass, and then solve for my acceleration. All right, so I went ahead and did mg, mass times 9.8, for my 8 kilogram mass minus the mg from my 5 kilogram mass, which left me with a net force of 29.4 newtons. Now, one of the key components to doing a pulley problem or an Atwood machine type problem is taking a look at the whole system. Remember, although we're maybe focused on the 8 kilogram mass moving, there's still the 5 kilogram mass moving along with it, and all of that are within our green system. So our total mass is 13 kilograms. So it's not just the 8 or the 5, it's going to be the 13 in total. So they set that equal to 13 times a, divided both sides by 13, and the acceleration of our entire system is 2.26 meters per second squared. Next, what I'm going to do is I'm going to do the pulley problem over here to the right, which is a lot more complex. So I'm going to start off with the similar steps that I did with this one, as in I'm going to draw my force diagram, identify my system, and then identify which way is positive and negative. All right, so this diagram got pretty complicated. So what I did is I drew all of my forces in red. So I have force of gravity down, normal force up perpendicular from the ramp, force of tension to the left up the ramp. And then for this object over here, we have the force of gravity down, tension up. And then I left out kinetic friction. So the question says, what is the acceleration of the 5 kilogram block if the coefficient of kinetic friction is 0.2? So because it's kinetic friction, I'm going to assume that it's sliding, but I don't know if the object necessarily is going to be sliding this way or if it's going to be sliding down this way. So if it's going to be sliding down the ramp, then friction is going to oppose it by pointing up the ramp. And then if it gets pulled by this object up the ramp, then the kinetic friction is going to be pointing down the ramp. So I'm going to reserve my vector for the kinetic friction for later until I see what's going on. So I made my system both of the masses just like I did with the previous one. And I have a couple forces going on. So what I want to do is I want to look at, again, which forces are external in the system. So I said everything going up and around this way is positive, and anything going back and down is going to be negative. So just like any kind of incline, we want to take a look at forces that aren't necessarily in the X and Y direction, but in the parallel and perpendicular direction. So I have two forces that are perpendicular. So my normal force and what I call the FGY, the Y component of my gravity. And then down this way, I have my FGX pointing down the ramp. And then opposing the system, I have an FG from my 2 kilogram mass. Okay, so what I'm going to do is I'm going to go ahead and set up all the sum of forces in the parallel and perpendicular direction and see what that leaves me with. All right, so what I did is I took my sum of forces in the perpendicular direction, which is just normal force up, and then FGY down. And if you set it up, it's Fn minus FGY equals 0 because there is no movement and definitely no acceleration in the perpendicular direction. So it's safe to say that equals 0. Therefore, the normal force is equal to whatever the FGY is. To find the FGY, all I would do is take the cosine of 25 degrees and then set that equal to FGY over the force of gravity of the 15 kilogram object, which is 15 times 9.8. So 15 times 9.8 is 147 newtons. You multiply both sides by 147 newtons, and then that's how I got the 133.23 newtons for the FGY. Now, looking at the parallel direction, that's where there's a little bit more going on because obviously the block is going to be moving parallel to the ramp in some way. So remember, I held on to which way the kinetic friction was going to go because I wasn't quite sure in the beginning. I saw for my x component similarly how I did this, except I did the sine of 25 degrees because opposite of this 25-degree angle is my FGX. So I set that equal to the FGX again over my hypotenuse, which is the force of gravity for the 15 kilogram mass, so 15 times 9.8, and then multiply both sides by 147 newtons because that's 15 times 9.8. All right, so I got 62.12 for my parallel component down the ramp, and then I have my negative component going up and around the bottom of the pulley resisting it, and that's only mass times the 9.8 of 2 kilograms, so 2 times 9.8 is 19.6, so it definitely looks like there's a lot more force directed down the ramp, which means that if the object is trying to slide down the ramp, then the friction is opposing it in what I call the negative direction along this pulley. So I can subtract then the force of kinetic friction from my FGX. Okay, so the way I'm going to find friction is on the side over here, I would do the coefficient of kinetic friction times normal force, the mu times the normal force, and I found the normal force a little bit early over here. So I'm going to do 0.2 times 133.23, and then I have my force of friction, which comes out to 26.65 newtons. All right, so now I pretty much have everything I need. I completed everything in the perpendicular section early on because there wasn't too much going on there. And then I wanted to wait to see which way friction was going to go. Turns out that it opposes the slide up the ramp against the block because it's sliding downwards. So what I can do is subtract all these numbers to get my net force, set that equal to m times a for my entire system. All right, so I took my FGX, which is my horizontal component from here, subtracted the FG2, and then subtracted the force of kinetic friction, and that left me with a net force of 15.87 newtons, and I set that equal to a mass of 17 kilograms, because remember, it's not just the 15 kilogram mass moving, it's attached to the 2 kilograms, so the total mass of the system is 17 kilograms. So net force equals m times a, divide both sides by the mass, and that left me with an acceleration of 0.93 meters per second squared. So I hope that was helpful in helping you understand, set up, and solve pulley and Atwood machine problems. Thank you for watching and listening.